Good morning and good afternoon, everyone. Today we are going to continue with our lateral dynamic study. In the last class, essentially, we looked at various tests that are conducted at steady state condition in order to find out vehicle handling characteristics. So there are three tests that we looked at: constant radius test, constant speed test, and constant steer angle test. So those tests were able to account various operating conditions of the vehicle as well as design aspects of the vehicle, so that you are able to get a practical handling tendency or vehicle handling behavior during steady state cornering. Why do we look at the steady state test and steady state cornering? Is because there is no transient state of the vehicle that is prolonged for longer time, right? Transient characteristic, of course, is important. How quick the transient response dies out is what is going to talk about the quality of your vehicle. But any time we expect the vehicle to be driven at a steady state condition, especially whenever you do high speed cornering. When you are doing it, you are expected to have your speed constant, and you go with the steady state motion. So at that time, the steady state gains, what you have studied, needs to be attained at the earliest. So when you give a steering input and you expect what is that to happen in your vehicle is the steady state gains are attained at the earliest. So there is some time interval. That time interval, vehicle actually will undergo a state called a transient state. At that time, you would have a transient response here vehicle, right? But that would be dying out quickly, and you would get that would dying out means that would settle down quickly, so that the vehicle would go with the steady state gains that are given. So what is the input that you give it to the vehicle would be a steering angle, and you expect your vehicle to go in a required curvature during the course. So this is all something in short to understand. We were looking at in the last class this test. Why the tests are important? How are they different from the characteristics that you can predict from a steady state governing equation of the bicycle model? In bicycle model, we make an important assumption that the model is linear time invariant model, right? So we have the tire model, linear model, and we were using steady state conditions. So time invariant parameters are there. So that is the reason why you have. So that also he expressed with the velocities as the parameters, lateral velocity and yaw velocity as two important parameters describing 2 degrees of freedom of your model and so on. And the most important assumption is the bicycle model is a rigid model, you say, because you do not account the flexibility of your vehicle that comes from the suspension system of your vehicle. So when you account that, you would have what is called this transient characteristics will be more pronounced in your vehicle. So along with that, you also have different operating conditions, like you can be suddenly giving traction or braking, or you see that there can be something called roll steer because of the suspension effect and combined steer and so on. So there are so many other aspects that are contributing to the variation of this understeer coefficient, and those contributions are transient variation. So those are called transient understeer gradient terms. So of course, when your vehicle is under steady state, it is predominantly depends upon your loads on the vehicle and the tire stiffness, lateral stiffness of the vehicle. What is that in bicycle model we consider is tire lateral stiffness are considered to be constant value, whereas in real time, if you look at the lateral stiffness of the tire is function of normal load. So it is actually a non-linear value. So as the load increases, you would have your variation in your lateral stiffness. So this is all something that you should understand clearly. But however, whatever the test that we have learned, or whatever the governing equation for steady state cornering through bicycle model that we have. All these things are very useful for to characterize and differentiate your vehicle handling behavior, so that you would rank this vehicle is much better handling characteristics than that of the other one. So that is the reason why you have to be clear with your lateral dynamic study. So today what are we going to do in our classes? We are going to look at some of the control system aspects, and we are going to get into stability analysis with the help of a bicycle model. So today's lecture will be more of generic, and then we will take that to gradually to our stability analysis, right? So let me share my board. So hope you are able to see and today's lecture. Number 30, and today's date is 13/04/2021. I'm going to talk on transfer function. See, we were doing it with the steady state gains, so which are attained by the vehicle when you give an input, that is steering input, and the steady state gains are the vehicle that is felt at t tends to infinity, or as the vehicle is entering into the steady state motion, right? So those are called a steady state gain, but those steady state gains are obtained from transfer function is what we have seen, and transfer function is an important parameter or important thing as far as control system design of your vehicle is concerned. So if you look at your advanced textbooks on vehicle dynamics with the control system, like automotive control system by Rajesh Rajamani textbook, and you see there are pure control system theory book like modern control engineering by Ogata. So this is all. If you look at, you see that vehicle dynamics and control system, if it goes hand in hand along with the signal processing, that you would become a multi-disciplinary engineer that you would become. So it is not only with the vehicle dynamics physics understanding one can survive, but with the appropriate understanding of your dynamics principle along with some control system knowledge and signal processing knowledge would give you better position in your career. But this course has got a lot of limitation. We are not going to get into automotive control system course. That itself is a course we can offer, or we can have signal processing for mechanical system, or vehicular signal processing itself is another course that has to be offered. So, but in our class, I would try to bring in the flavor of this control system idea, which I do referred with the modern control engineering by Ogata textbook, and that you'll feel that you should not feel that this control system is tough or something. You should feel that it's simple, and we'll look at that and then get into our dynamics part, how they are connected. We will see that, right? So if you look at the transfer function as according to control theory, right? Transfer functions from control theory, if you look at, you would have three transfer function. One is called open loop transfer function. Another one is called feed forward transfer function, and another one is called closed loop transfer function. So you should understand what are these transfer functions. For any mechanical system, you can represent the system to be some order of system. So for example, heat transfer problem can be looked at as a first order system, our vibrational problem can be looked at as a second order system. So like that, if you see, any mechanical system can be represented as an nth order system. So nth order system would be represented by nth order differential equation, right? Like a second order system of your forced vibration study, what is that equation that we have? Mx double dot plus kx cx dot plus kx equal to some forcing function f of t or u of t that we say. So if you see, that is of second order ordinary differential equation. So if I have my input 0, then it is for free vibration, which is essentially for stability analysis that we look at it, right? So like that, you can have your mechanical system can be described by a differential equation of order of the system, right? So that system again can be of linear system, non-linear system, or it is a time invariant system or time varying system. It's called a causal system or non-causal system. So these are all the definitions. Please refer to the control system textbook and then please get familiar with them. So how do you define these systems, right? So what is that we are going to look at now? Control system theory is the linear time invariant system. For linear time invariant system, LTI system that we call. What is it? Linear time invariant system. You can represent that system by a block having a transfer function represented here. Say that is given by, see these notations, you should not get confused. Textbook to textbook it may vary. Please follow that, right? So G of S, so it's what is called a transfer function, and you see there will be an output, there will be an input. So your vehicle can be considered to be a block box with the transfer function, and there will be an input and there will be an output, right? So this input is generally you call it as U of S, and then output, say I call it as an X of S. So now what is this transfer function? This transfer function is defined by output by input, right? So therefore that output can be now written as G of S into U of S. What is S, by the way? Here is S is Laplace variable, right? So if this is your control system design, see, if we have a transfer function, it is going to involve the products. So you have your transfer function multiplying with the input function, then you get your output function. But it is in Laplace domain. So you want to get this output as function of time. So what is that you have to do is, you have to take an integral called Duhamel integral or convolution integral. So that will be, this will be in function of time. If you want to get, that would be from 0 to t time, you have to integrate. So G of t, or it can be written as G of tau. G of tau, it's a time step, time delay step. G of tau into U of t minus tau into d tau. So this is that integral you would get. Or you can also write this as 0 to t U of tau G of t minus tau d tau. So this is what is your output response you will get, right? So both U of t and G of t are 0. U of t and G of t's are 0 when t is less than 0. That means from the initial condition only, see, initially it is 0, that is the meaning. Then it is going to have with your input function, accordingly the output function. So if U of S is happen to be, input is happen to be unit input, right? If U of S happens to be 1, then what is going to be my X of S is simply the transfer function G of S. That is what we will always, to find out any mechanical system, its transfer function, we will give an unit step, unit impulse function. So the magnitude of that function is 1. So that would be unit impulse function. So when you give an unit impulse function, you get your output. That is what is going to be your transfer function, right? So then x of t will be simply Laplace inverse of this x of s. So that's going to be simply g of t. So what is g of t? Is what is called an impulse response function. Impulse response function. Also, this function, some textbook called weighting function of the system, right? So this g of t for the is the response of LTA system to an unit impulse input. That's what you have to see. So this is obtained from unit impulse input. Unit impulse input when the initial conditions are 0. When the initial conditions are 0. So this is what is very important. That is what we will do in our laboratory test called a hammer test. So we have a hammer where it is nothing but a sensor mounted at the tip of the hammer. 4 transducers there. So when you excite that with the mechanical system and you have a sensor mounted adjacent to that, you would get your drive point response, and that response is what is called impulse response. So it's what's called an impulse response function in time domain. If I take that Fourier transform of my impulse response function, what do I get is called a frequency response function. If I do take Laplace transform of my impulse response function, what do I get is what is called a transfer function. So this is how you would get simply for a mechanical system the transfer function measurement, right? So this you should understand. So now what are these 3 transfer functions that we have termed at the beginning? So let us look at them. So for that, let us look at see, now this is kind of how does it appear is like a open loop. There is no loop. See, whatever input you give, you get an output, and there is a system. Entire system is represented by a transfer function. So you can call this as an open loop transfer function, right? However, let us look at an actual control system. How does it work when it is happened to be a closed loop control system? So if you look at in a control system design representation, schematic representation, there is an important point called the summing point. So you would have here the signals coming in and get added. So there is plus, minus. So this is again minus, plus, like that, right? Let's have it here only with this. So like this. So now you see that there is an input signal that comes to this summing point, and that signal let us call as per the textbook Ogata textbook R of S. That's an input, and this has got go with the transfer function G of S. Since it is a closed loop design, so we call this transfer function as feed forward transfer function. Feed forward transfer function. And then you go, you get your output, which is your C of S, right? So now if you look at this is whatever input you give, you get an output. It is not correct. You feel there are errors, then you want to correct them. Then you would take a feedback from here, a signal feedback, and that would go through another transfer function here, what is called a feedback transfer function. This is called H of S. I call this H of S as feedback transfer function. Right? And then from here you get a signal out. That signal will be taken to this summing point. If this is that error that has to be subtracted from my input and corrected, I will get my corrected signal here out of the summation point. This is what is E of S. And here what is that I get into that going is what is called B of S. So what is B of S here is corrected or feedback signal. This is feedback signal. Feedback signal. But the feedback signal is taken from the output that goes through the feedback transfer function, get multiplied, and that I get B of S. And now R of S and B of S difference is what is my E of S, and that goes again here and this. So this is what is a representation of a closed loop control system design of a mechanical system. So in this, let us now define what are our open loop transfer function. Open loop transfer function. So what is my open loop transfer function? I have here, this is my feedback signal. So I take my feedback signal, and what is that has gone here is E of S. So B of S by E of S is what is called an open loop transfer function. B of S by E of S is what is called open loop transfer function. So what is B of S is feedback signal divided by E of S is what? Actuating error signal. That is an actuating error signal. So it is feedback signal by actuating error signal is what is open loop transfer function. See, in this open loop transfer function, again you look at the B of S comes from this output. So what is that output? It is C of S here. I take that and I multiply with the H of S is what is B of S. So it is H of S and C of S is what is B of S. Feedback signal, how do we get? Take an output, signal from an output, and that has to be sent through a feedback transfer function, so that I will get my feedback signal, and that is what is now represented by this and divided by E of S. So now what is C of S and E of S? C of S and E of S. This, if you look at, what is that? That's going to be, look at here, C of S is this and E of S is this. So if I take this output, this is an input, and this is G of S. So I would write this as H of S into G of S. H of S into G of S. That's what is my open loop transfer function. So you may ask, then you said that here, this is G of S is your open loop transfer function. That's correct. When H of S is unit value, then open loop transfer function is simply H of S, right? So you can see that here.
Sir?
So, yeah.
Sir, I thought the first diagram was an open loop and this should be closed loop because there's a feedback.
There is. That's correct. This is open loop system. There is no feedback taken. So this is a simple representation of open loop system. So what is that example of your passenger car open loop control system study? That you drive your vehicle and you suddenly give a step input steering, and then you see what is the output. So that is what is your open loop system. Instead of that, if I give a pulse input, that's what I was telling. I want to find my transfer function of my vehicle. What do I do? I'll take my vehicle, go in a straight path where I have my skid pad, where it is very large, flat surface track. So I just go and then I give a pulse. So what do you mean by pulse steering? I'm not going to give a steer angle and hold it. That is step input. I just give a steer angle, hold the steer angle. That is step input. But I'm not going to do that. Instead, I give a pulse steer input, and that pulse steer input, if I give, I would get my transfer function, right? That's what is that I was telling, analogous to having a hammer and having a physical mechanical system in the laboratory and give an excitation and then get the response, you get your transfer function. Same way, to get your transfer function of your vehicle for a handling study, what is that you have to do is give an impulse steer input, pulse steer input, so that what is that you get would be your transfer function that would define the output. What you get would be your transfer function, because when you give a pulse to your input, it may not be unit pulse input exactly, but you would have some value, so you can get your equivalence of your unit pulse input. When I excite by hammer, I'm not going to give exactly 1 Newton. When I excite, it may be 2 Newton, 3 Newton force. Gently I will excite. But all the time giving 1 Newton is not possible, but it is a scaled value. So what is that I get would be my transfer function. So what is this first diagram drawn is open loop system. You rightly said. So this is open loop system.
So the ratio that you gave BS to ES, that is for the closed loop, right? Because there's a feedback signal.
There we are defining. So here it is. Just 1 minute, I'll come back. This is closed loop system. Right? So here, this ratio what we have defined, here is what is open loop transfer function, I said, right? Open loop transfer function in closed system only. But you see now here, my feedback is 1 here. Here itself, again, you are defining this open loop transfer function is nothing but your G of S, where this G of S in our closed loop system is feed forward transfer function. Feed forward transfer function, right? So that is in a closed loop control system, open loop transfer function is G of S. So when it is, if H of S, if my H of S, which is equal to 1. So H of S is what? It is a feedback transfer function. If feedback transfer function is 1, that means whatever that I get output, that itself is taken as my input here, reference, right? So if this is 1, I would have here C of S by E of S is going to be by G of S, because this happens to be 1. So you would see that in some design, this H of S is not going to be there only. This output signal will be taken straight away and put here. So here you have an input. So what do you mean by that? Any control system design, closed loop system design should get into its steady state. For example, I give my steering input. I know that I require to go in this exact curvature, right, for a constant speed. But when I give my steering input, it is not going to happen immediately. It will have to pass that time of transient duration. So when it attains its steady state, what does that mean? So whatever my input I give, that same would be the output response, right? My intention is, what is that input? My wheel should have a steering angle turn at the interaction of the road. Appropriately, I give my steering wheel rotation, and that angle should be maintained to go in a car if my vehicle is of neutral steer vehicle, you are saying. So that is steady state. So to attain that or not to see, you will always take a feedback to compare. So that is what is happening. So this feedback signal and your input difference is 0, then it is attained. The output is it is reached to the steady state. It is not so, then there will be a correction that will keep coming. So I will look at my output. What is that? Is it accordance with my given input or not? To see, I will take a feedback and then I will give, and then that system is what is called closed loop system, right? Is that clear?
Yes, sir. So could you just tell me what ES is? The
ES is what is an actuating error signal.
Error signal.
So,
okay, sir.
So what is that? Error is 0, or error is 1%, error is 2% is what is that outcome, right? That is what is that signal is E of S is called actuating error signal. That is summation of your input and your feedback signal, right?
Okay, sir.
Yeah. So now again, how do you get to define your closed loop transfer function? So this is open loop transfer function, as same as that of feed forward transfer function. In case you have your feedback transfer function value is 1. If this is 1, otherwise it will be product of H of S and G of S. Look at it; it's important, right? And now, what is closed loop transfer function? For that, how do you define closed loop transfer function? Is whatever that I get my final output and to that of input given is what is my closed loop transfer function. So closed loop transfer function in a closed loop system is nothing but C of S by R of S. So we are going to have this transfer function only in our study. So this can be derived nicely again from the system. What is C of S? So this C of S would be from here E of S into G of S. It is E of S into G of S. And what is R of S? I'll just before substituting here, let me just play around with this. So what is E of S? E of S is R of S minus D of S. So you are asking about what is E of S. E of S is my input and subtracting my feedback signal. So that's going to be R of S minus B of S within bracket into G of S. Right. So now what is B of S? We come from here, it is C of S into H of S. So it is going to be now again R of S minus B of S is C of S into H of S. And this within bracket, and I have this G of S out. So now again you look at, I just take this G of S inside, so let me multiply that R of S into G of S minus C of S, H of S into G of S. And now you see, I'm going to group C of S together. See, what is that? My interest is to get this ratio, right? So here I have C of S here appearing and C of S on this side. So let me take this term on this side. So it's going to be C of S. That's going to be R of S, G of S. If I take that out here, bring that out here, that's going to be 1 plus G of S, H of S, right? So now what is my closed loop transfer function? That's going to be C of S by R of S. So from this, I would write that as G of S by 1 plus G of S into H of S. So this is what is my closed loop transfer function. So in this, what is G of S is? G of S can be open loop transfer function in case of H of S is 1, we call it as. Otherwise, we call that in closed loop control system. And the right term is feed forward transfer function. So if I have my feed forward transfer function, feedback transfer function, I will get my closed loop transfer function like this, right? So this is how you define what is your closed loop transfer function. So we have understood now what do you mean by open loop system, what do you mean by closed loop system, right? And in the process, we have looked at open loop transfer function, which can be defined in open loop system as well as in a closed loop system. So open loop system, whatever you define, is what is that we are going to look at it as a response study, right? Okay, so now let's just continue doing that further. See, if I have my mechanical system is of nth order system, how do I represent nth order system, right? So if the system is of nth order. So how do I represent that by differential equation is this? So that would be A naught d power n x by dt power n plus A1 d power n minus 1 x by dt power n minus 1 plus A2 d power n minus 2 x by dt power n minus 2 plus and so on, plus I would have here A1 like that it goes, so I will have a term A n minus 1 dx by dt plus A n x. So this is what is my nth order differential equation representing nth order system. we are not going to look at so many this nth order systems, very generic form, but our dynamic study is all confined with the second order system itself, right? However, let us just look at this control theory can accommodate any complex mechanical system comfortably to look at and analyze it. That is what to understand. We have to understand always from a generic form. So this would be on my left hand side. This would be equal to, this is equal to, on the right hand side, if I put 0, then it is a homogeneous system. So nth order ordinary differential system, where if I make on the right hand side 0, but I will have a forcing function, and that forcing function would also be represented by a differential equation. So let us put that as b naught d power m u by dt power m plus b1 d power m minus 1 u by dt power m minus 1 plus and so on, plus you would say that it is b m minus 1 du by dt plus bn into u, bm into u. So in this, if you look at this m, the order of this is the nth order system, this is nth order input forcing function. So this m order should be less than or equal to n. That's a condition, right? Always. So now if I have, this is a generic mechanical system of nth order, then it's not only mechanical system. It is a system means it can be not only mechanical system. That means it is a electrical system, or it is a mechanical system with heat transfer. So many physical phenomena. That's what is the nth order system. You could say mechanical is very specific because you can also have an electric system and so on, right? So you can say in the system of nth order. So that would be a combination of all. So nth order, then I can represent that to be like this. So in this case, if I have to get my control system transfer function, that is C of S by R of S, which is my closed loop transfer function. Closed loop transfer function. So that would be how that is my closed loop transfer function is because I look at it my system now plus minus, and I would have this transfer function here, which is open loop transfer function I write because I'm not going to take no feedback transfer function. It is unit. So this is my system. So this is R of S, and when this comes, you have here E of S, and this is C of S. So this is output and this is an input. This ratio for this unit input, whatever that I have, is what is again a closed loop transfer function. That would be simply obtained for the nth order system if I take numerator and denominator Laplace transform with the initial conditions, zero initial conditions, then I would have my C of S by R of S is going to be ratio of two polynomials. That's what I was telling. So what is the polynomial that's going to be here is, see, if I take this equation, differential equation, LHS and RHS, Laplace transform with the initial zero conditions. Initial conditions are zero. Then I would have the ratios here where it's B naught S power M plus B1 S power M minus 1 plus B2 S power M minus 2 plus and so on plus Bm minus 1 S plus Bm divided by A naught S power N plus A1 S power N minus 1 plus A2 S power N minus 2 plus and so on plus An minus 1 S plus A naught, sorry, An. Right, so this is what is my transfer function. So if you look at for that matter of second order system of a mechanical vibrating system, what is that equation that we have? for example, second order ordinary differential equation mx double dot plus cx dot plus kx equals to u of t that I take, right? So here this e of t is again a function of time. So I take this here. So this e of t can be 0 for eigenvalue problem or perturbation analysis to look at the stability of your system or to find out the natural characteristic of the system, right? If I put my forcing function here, e of t is an impulse function, then I will get my transfer function. If I put my unit step function, I'll get according. If I put a harmonic excitation, I'll get my x will be a harmonic function. So whatever that function that I get, accordingly I will get my output response. So that output is what? X of t. Output response, right? I will get for the given input function e of t. Correct? That is my second order system. So why do I take the second order system now is because how do you represent now for this in this form is what we will understand, right? That's where the representation of state space form is very important, very easier. See, this all we define. So you may ask how these functions are come here. So what is that in this box, this transfer function, how does it come? So you would say that transfer function is this ratio of this polynomial. How are these polynomials have come? Is what is your question. So if that is that, then let me write your final answer, then we will go into it. How do we get it, right? C of S by R of S would be for this system is omega n squared by S squared plus 2 zeta omega n S plus omega n square. So this is what is your transfer function you would get for this second order system. For this second order system. How that you can get that? See, you can see here again this order here S squared, here there is no S. That means you can have m less than n. So m less than n means that transfer function is strictly proper transfer function, right? You have transfer functions are called proper transfer function, strictly proper transfer function. 1 minute. So return down that sound. Just a minute. Yeah. So in this, if m is less than n, then it is strictly proper transfer function. Strictly proper transfer function. This is case 2, right? If I have m is less than or equal to n, less than or equal to n, that means it can also be equal to n. So the order here of this polynomial, see, this become polynomial equation, right? So n order n is equal to m, then it is called as proper transfer function. If this is a condition, then it is called proper transfer function. Whereas if m is less, then it is called a strictly proper transfer function. So you would see that always the numerator polynomial order is smaller than that of denominator polynomial order. And the denominator polynomial is very, very important. That denominator polynomial is what is actually Si minus A that we have looked at, determinant of this, right? That polynomial is what is that is there in denominator. You have to connect all of them. So if I have my A, what is A here is state matrix. If I have the state matrix of my second order system, I would be able to derive this transfer function. That's what I'm saying. So if that is that you understood, you would appreciate an advantage of having state matrix, advantage of representing as a state equation, state space representation. So what does a state space representation does? If I have nth order system, that would divide the system orders into n single order system, and I will have n single order equations, and that is what is going to have a lot of advantage in control system design. That is why if you open any control system design textbook in first module itself, you would have this all things to be explained that you should understand, right? So now let us continue with that. How do I get my this transfer function? That's what I'll explain with this simple well-known second order system of vibrating system. So what is this equation? This is physically how do you represent? It can be represented by a spring and dash part with the mass, right? This is K and this is C, and your forcing function is E of T here. So if I draw this upside down, then an entire vehicle mass is just kept on this. So all the suspension I can take, I can neglect. No, I can write my. If I look at my unsprung mass and then sprung mass, there are we will see that in detail in our ride dynamics part. So I can also represent my vehicle as a single degree freedom model. So if I consider that, I can work out for this bounce. Then for next detailed model is what is called quarter car model and so on. That we will see as a vibration model separately. But now if I have this equation, how do I get my transfer function? For that I would represent this second order system as a state space form. So how do I represent that? That is what I will just explain you now. And then we will proceed with our class. So now, so look at that. I have now, this is my equation, right? The mx double dot plus cx dot plus kx. Some of you could have done your control system study in your undergraduation. No, then you would know this. In case you have not done, you don't need to worry. It is simple. Please open the textbook. Ogata, if you open and you start reading, you would stop reading Wong textbook and you will be so much immersed into that book. So very interesting. And you would also see that MATLAB commands can be, how can you use for getting these responses. All are explained very well in those books. Ogata, Modern Control Engineering, and also Automotive Control System by Rajesh Rajamani. These are the textbook. If you can refer, you would have a complete hold of control system understanding, and you can use your MATLAB for that purpose, right? So just let us look at now. This is our second order system, and I am going to represent play around with this variable. So I know my output is x of t. So I am going to represent that x, my output, as x1, right? The x1, and then the rate of change of this output x dot as what is that is going to be x1 of x1 dot, that's going to be x2. Then rate of change of x dot is what is x double dot. I'm going to have this x2 dot. That's all. So this is how I just represent. So my output I am just representing to be an x1, which is one of the state variable, and x2 is the second state variable. So I'm going to use this x1, x2 as two state variable and represent my second order system by two single order system equations. That's all. So that is what we straight away deduced in our bicycle model. Bicycle model, we had our v dot, r dot, the equations, the two equations, right? What are Fy is equal to mv dot plus ru, and then the second equation mzz is equal to izzr, right? My is equal to izzr. So those two equations, governing equation, we were able to represent as a in a bicycle model as a state space form straight away by putting those parameters, vehicle parameters. But now when you have this three parameters, C, K, M of a single degree freedom system, which is represented by a second order system, I can represent that with this. So that I would have now this equation. So what is my first derivative of state variable x1 dot? So x1 dot, you look at x1 dot as x2. That is my first equation, state equation. What is my second equation? I have to get x2 dot. Like v dot, r dot we had, here x1 dot and x2 dot. So what is x2 dot? X2 dot is x double dot, or x2 dot would be, how do I get x2 dot? X double dot. So x double dot, I'm going to get it from here. X double dot, I'm going to get it from here. So from this, I can get what is x double dot, right? So divide by m all, so x double dot, and that would be equal to u of t by m minus c by m x dot. So x dot is what? X1 dot. So x dot is x1 dot, right? So this is just first let me write that here, whatever is there here. That's going to be x dot minus k by m x. So if you look at here, x2 dot is what is x double dot. I'm going to write here now this equation as this. So it is u of t by m and minus c by m, or x is what is x1. So let me take this term first. So minus k by m, x is what is x1 here, see. So x1 minus c by m, x dot is what is x2. So this is what is my second equation. So these are the two single order equations. See, now I have x1 dot, x2 dot. These are first derivative, single derivative, two single order systems, where x1, x2 are my state variable. So this two equation can be combined and can be written in the required form. So I would rewrite this as x1 dot, x2 dot, because I want to write it in this form. What is that form? Q dot, or here it is x, right? So let me write it as x dot is equal to a into x plus bu, right? Bu. In this form I want to write. That is what is my state equation. So you can combine these two equations. Now we can see this x1 dot, x2 dot is equal to, what is my A matrix? Supposed to be for having x1, x2 as my state variable. So first equation is x2. So x1 is not there here. That means I should have here 0 element and here 1 element. So see, look at now, x1 dot is equal to x2. I get my equation. And I should not have any other term. So plus here also my b vector, I should have here 0, and this is u of t, right? Right. Then second equation, we look at here u of t. So u of t, what is the coefficient? 1 by m. So that should be here 1 by m. And x1 coefficient minus k by m. So x1 coefficient is minus k by m. So here it is k by m and minus c by m. Minus c by m. So now this is my 2 by 2 state matrix. For the second order system, my state matrix is 0, 1 minus k by m minus c by m. Like this we had for a bicycle model as well, you remember, right? We had 4 elements, but that was expressed in terms of vehicle parameters, tire parameter, and so on, right? Of course, the forward speed also was there inside that. So you could recollect that equation of bicycle model, A matrix. So this is my B vector, which is 2 by 1, right? So now what is my second equation? State space representation means this is my state equation, and my output equation is what is second one. So this is my first equation, Roman letter 1, and then my second equation is my output equation. So output here is x response. So that would be, what is x is x1. So I would have that as 1, 0 dot product with x1, x2. So like that I will represent. So x is equal to x1 is what is my second equation, and I call that as an output equation. So this is a simple representation of second order system into two single order system. So if that is possible, I can also make my nth order system into n single order system, right? Okay. So now here to continue with that, see, this is what going to help you to develop a block diagram for your control system design. So what simulating that you are doing it, you are adding some integrators and so on, and you get your response, right? So that let us just represent your state equation, this output equation what you got, with respect, with the help of that, let us represent that now our control system design for this. So I would have my summing point plus minus, and I would have my R of S. So here R of S is what is my input, right? So R of S is what is in this input, and I would have that here given by U of T into this. That's my input. So I would have my U of T, and I would have here beforehand multiplier. So 1 by m, it is multiplier and it comes here. So that's my input to the system. And the output of that would be what I would have here. First I would have my x double dot. So x double dot is x2 dot. x2 dot is what is x double dot. And that has to be integrated because I want to get my x. So x double dot is what is first will be integrated to get x dot. So what is my x dot? Of course, x dot is x1 dot. That's x1 dot. x1 dot, or that is equal to x2, right? That's what we were writing. That's equal to x2. So again, this x dot, if I send through an integrator, I would have x. So what is x1? So I would have my x1, which is my output. So look at in this output equation, x is equal to x1. That's my output. So this is my output. So now you see that in between what are my other transfer functions or the parameters that are to be implemented. So you see that whatever that I get here, x2. So x2 into, look at my equation, x2 into minus k by m, x2 into minus c by m should come. So I should get x1 into k by m. So this x1, I take an output, and I can vary this parameter. That's what we are looking at, right? So this parameter minus k by m should be there. So I would send through that minus k by m. And take this where? To my summing point. So if I have here minus sign, here it's minus become plus. So I should have here k by m plus, and that is to be taken here, right? And similarly, you see here x2. So x2 into minus c by m. So I'll have to take from here on out, and that has to go. And this would be again here. What is that I should have? This is plus minus, and this is plus terminal, and this is minus terminal. Then I should have here minus c by m, and I should take it like this. So now this is what is my simple control system design for second order system to get an output, right? To get an output. So now this is block diagram, control system block diagram. So how do you go about getting this is what you have to understand. How do you go about getting this omega n squared by s squared by 2 zeta? So you know what is zeta is damping ratio. Omega n is natural frequency. Yes, omega n squared. So this is what you have to get. So that can be obtained very well from your state space representation of this equation. That I would explain in the next class and continue. At this point of time, I will stop the lecture. If you have any doubts, you can ask. Right? Then we will continue with that. We'll see that how can you use state matrix, and from this state equation and output equation, how can I get my control this closed loop transfer function, this transfer function. So if I get that, then I can get that same strategy applied on my bicycle model, because I have my A matrix, I can get my transfer functions. So if you have a transfer function, you would be able to get your output response, right? Yeah. For any given other inputs. So any doubts? If you do not have any doubts, I will stop at this point.